Good morning, students. Today we will study about the potential energy of a spring, for which we have considered an elastic spring of negligibly small mass. Its one end is attached to a rigid support and the other to a block of mass m. This mass m can slide over this smooth horizontal surface. Now, when we compress or stretch the spring from its normal position by a small amount of distance x, then a restoring force is developed in the spring, which tries to bring back to the spring into its normal position. From the Hooke's law states that the restoring force which is developed in the spring F, it is proportional to the displacement under elastic condition. This means the restoring force F is directly proportional to the displacement, or this F can be written as minus kx. Here k is a constant which is known as force constant. Here the negative sign indicates that the restoring force is directed towards the equilibrium position, and this coefficient of this coefficient is known as spring constant, and this spring constant can be defined as force per unit length. Its SI unit is Newton per meter. Because this external force is equal to the restoring force and opposite in direction, so F external is equal to minus of restoring force. Now, on substituting the value from equation number 1, we will get F external as minus of minus kx, which will give us kx. Let the spring is displaced through a small distance dx. It is displaced through a small distance dx. Then the work done by the spring, force, dw is equals to F external dot dx, or it is equal to F external dx cos 0, because the angle between force and displacement is 0 degree. So this small amount of work done can be written as dw is equals to kx dx. So the total work done to stretch the spring from normal position to a distance x means from x barabar 0 to x is equals to x, the work done it can be obtained by integrating this within the limits x is equals to 0 to x is equals to x, kx dx. Because this k is constant, so it will come outside the integration, and this will kx dx, limit 0 to x. On integrating this x, we will get x square upon 2, and the limits are 0 to x. So the value of work done, W, will be equal to half kx square. And this work done will be stored in the spring in form of potential energy. So the potential energy of spring, U, is equal to the work done, or it is equal to half kx square. So this is the formula for potential energy of a spring when it is stressed or compressed.